when I was playing the Hello Quantum game, there was an article to a Medium. There was a link to a Medium article, which was, I think, it's supposed to give an introduction to the IBM quantum experience. So it's not this article, but I found this article which is basically about the Hello Quantum game, I think. And as I didn't really fully understand some of the concepts in there, I believe, I'm hoping that this is gonna really help me. Help me understand that. So let's see what happens. Let's get some color in there. So basically, if you want to start playing with quantum computers, you've got to play. Best practice tutorial will be an interactive experience. Yeah, okay, the very basics. I think we can just scroll over that. Forget quantum computers, no computers, true, false, zeros and ones, and on-offs. So this is the standard introduction. By the way, so Dr. James Wooton, I hope I'm pronouncing the surname correctly. I think he is one of the main brain and developer behind the Hello Quantum game. So I think the contents of this article could be good. Okay, so asking qubits questions. Okay, that was also explained, and it seems like the same. It seems like the same images are being used. So that was also, I think, part of the learn more guide within the game. The process of getting a bit, essentially asking a question. So you can ask, and then it turns 0 or 1. So 0 or 1. Over the last few decades of studying qubits, the possible questions have become our favorites. Don't fully like that language about asking questions and whatnot, but I guess it might make it easy to maybe explain. It's sort of an analogy, right? Because talking about measurements can be confusing for people, I guess. Why? I mean, I don't know. So despite our infinite set of choices, we usually just pick one of these. One of the questions is to ask the bottom circle, is it black or is it white? And the other question is to ask the same thing about the top one. So you see, that's following the same style like within the game. The only problem that I have with that is that you're kind of sugarcoating something here, right? Which is it's the same qubit, right? And then this is just what do you see if you measure it in a certain way and if you measure it in another way. So, but let's go forward, asking questions. Experience. I have been playing a little bit with that, but I'm gonna definitely make an extensive set of videos about the quantum experience. The IBM quantum experience, because I think it has one of the most and the best interesting tools to build up intuition about quantum computing. The IBM experience represents quantum programs using a collection of lines. So this is, and he basically introducing the concept of a circuit. Here's the one you need to ask about a qubit's bottom circle. Yeah, so we see this is the so here we have off, so it's always 0. This is white, and on, so it's always 1. And here we have like the uncertainty. But what we know, given data, if I remember this well, is that this is after applying a Hadamard gate, and it's off, so it's a 0. But if you measure them this way, you get equal probabilities 0 and 1. Yeah, so that's the okay. So that's the next measurement. That's how you measure the qubit at the top, so to say. Okay, so you got the same examples, right? So there's the same examples, but in this case, you've got now you measure that, and here you measure. Oh no, it's not the same examples, but okay, the same outcomes in this case: 0, 1. And here, despite the fact that if we measure it in the previous way, we know it's off, then if you do Hadamard, it's both so equal probability 0 and 1. You might have noticed something in the images above. When the top circle is certain, yeah, okay, that's so that thing here is an interesting concept. So basically what they're saying is that when the top circle is certain of the answer, the bottom circle is completely uncertain, and vice versa. that is definitely helpful, because it gives a view on what's the nature of a qubit, right? So you're playing with certainty and uncertainty, and if you move this certainty and uncertainty around. This is because a qubit can only be certain of its answer to one question at a time. To one question at a time. Okay. Fundamental uncertainty in quantum systems. Okay. Okay, but that's what I'm interested in now exactly. So what happens with two qubits? And you see here we don't have here we don't have anything here in the middle. And in the game we did have a grid, and I really definitely want to know what this grid means. I've got an idea, but let's see. So far, it's just let's play with two qubits at once. So it's the same way, but like, yeah, exactly like that. So thanks to the constantly present randomness, this description isn't good enough. Good. Oh, that's getting interesting. So thanks to the constantly present randomness, this description isn't good enough. For example, here's something we can do with a couple of qubits before they get measured. Okay, so this part over here is creating the bell state. So that's creating an entangled state that it constantly agrees. So you can only measure both zeros and or ones, so to say. This we know from other examples. This little quantum program for two qubits, okay, we'll get around to explaining all these components later. Yeah, I mean, okay, it's basically saying forget about the gates for the moment. So, okay, after we run this program, let's ask both qubits about their bottom circles. So what's happening here? Okay, so we've got the circuit everywhere, and then okay, and we're asking all the questions. So that's these two are without a Hadamard, and these are with a Hadamard. So here's here you've got the question, here you've got the question, the measurement, so to say, right? And then so in this case, this qubit in here can be both 0 and 1, 50% probability, the same one with the second qubit in the system. And if you do the same here, you get the same. I see. So it's trying to say where is the certainty and where is the uncertainty. And no matter how we measure that, we see there's uncertainty everywhere. Here there's uncertainty, there's uncertainty, there's uncertainty here. So they're all random. So according to that, this means that the way the circles would look like that. So that's the starting point. That's the starting point, and then basically this is saying so what we have that. So where is the certainty? Where has the certainty gone? That's a cool way of looking at things. Okay. So and that has probably moved in the grid in here. Okay, and this is that's a really neat way of showing that. Okay, because here all we're doing is we're asking questions to independent qubits, and of course you see that each qubit is completely uncertain. That's cool, nice. But when you ask both at the same time, so you're measuring the system, the overall system, then you see where this is 0, 0, 1, 1. Beautiful. So this is where the information has gone, right? So though the bottom circles give both random answers, those answers are certain to agree. Nice. That is definitely something. So, okay. So what this is saying is they give you random answers, but they're going to agree, right? It will independently give you zeros and ones, but measured together, they will always agree. So they're both zeros or both ones, and that's the correlation, right? So that's entanglement, and this is a pretty strange thing that happened. The qubits truly didn't know how they would answer these questions until we asked them, but somehow they conspired to always agree. Accounting for effects like this is going to require some extra detail in our visualization for the qubit states. We need to keep track of whether the answers given by the two qubits agree or disagree, and we need to do that for all possible pairs of questions. Okay, I see. So this is what we're adding now. This guy here, which I think when I was playing the game, I got to a similar conclusion where I said that probably means this is probably encoding information about whether they agree or not. And it was confusing because I was not sure whether the black so off means agreement or disagreement. Okay, but here they say when the color is black, then they're certain to agree. That's the I guess the convention. So, and now if we try to ask both qubits about their top circle, you'll find that they always disagree. So before it was here and here, and now they're both gone in the middle after applying a Hadamard gate. I still have that I feel uncomfortable with this concept of understanding this as a measurement, rather than saying no. For me, I'm always going to measure this way. So I'm just gonna and consider those part of the algorithm, right? Not part of the measurement. But I understand why you could think about this in that other way. Okay. Interesting. So we'll need to add another circle to represent these. Okay. So yeah. So in this case, because you have the top circles and those refer to these, whether they agree or disagree, and then you have the bottom circle, which is whether those guys agree or disagree. Okay, that's interesting. So what about this? I'm guessing that probably might be whether these and these agree or disagree. Although that's that's a lot of stuff you can really encode in here, honestly. That's cool. Okay, I get it. Let's move forward. You could ask one qubit about its top circle and the other qubit about its bottom circle. No. Yeah, okay, of course. Yeah, that's what I just said. That would be basically the top and this bottom. That looks like a mess. I see. So, and what happens when you do that is that you get. So if you try these combinations of measurements, you will find that they are equally likely to agree or disagree. Okay, so they are kind of random in that sense, right? Okay, random. Yeah, so this and this. It's super interesting. Okay, super interesting. Given qubits answers. A picture gives us a full description. Okay, so good. So we know that. So this basically, this thing in the middle in the game encodes the type. So how the correlation between the qubits? So this is one qubit. This is one qubit. This is another qubit, and this is the correlations about those qubits. But we have to remember that these dimensions here, they are basically it's the same qubit, but measured after a Hadamard. Interesting. That can be complicated. I guess it's going to be complicated to intuitively build algorithms at a higher level in terms of an amount of qubits and stuff like that, because this is tricky to represent and know what's going on. So maybe there is a way maybe there is a better way to build intuition. But I get those concepts. That's really super useful. Giving qubits answers 0. Yeah, okay. So this is again the guide. So that portion here, right? Why is that not in the guide? Why is that not in the? Yeah, maybe it's too. Of course, maybe it's too. Um, it's too technical for the game. Maybe they consider it too technical for the game. Like you don't want to show necessarily all that stuff. But I mean, it definitely helps if you're trying to build intuition. And I guess people are going to play the game to build up a bit of intuition. Um, and so 2 qubits at the beginning of their lives look like that. Hmm. Okay, so that's how they look at the beginning of their life. This means, yeah, and again, that tells you, it's not that they're entangled or anything, but it tells you they will always agree if you measure both of them. When you look at 0, you're probably wondering about this and this. Okay, that's just the bracket notation. Forever kind of, so and now introducing the notion of gates, and here we have the X gate to basically flip that. Okay, state 1. Changing the bottom circle of a qubit also affects how it relates to other qubits, of course, and that's why this changes as well, right? So now they disagree. Okay. Now they disagree, and the same here. They disagree, and then that is though that is an interesting way of seeing the Z. Oh yeah, of course. If I take a look at, yeah, because if I think about the Bloch sphere, that's what the Z does, is that it's basically going from the plus state to the minus state. And if that sounded like something you had no idea what I'm talking about, check out my other videos. There's a video on the Bloch sphere that I did, which gives you an introduction. Sometimes we might also flip the top circle, but that's cool. So that's a way to intuitively think about it. Is so what the Z does. What the Z does is it basically flips the it flips whatever information you would have in the whatever. I don't know how to call that. Because it's like it's in another, it's is it basis, am I using the right terminology, like so I've read this somewhere, so that's a measurement basis, right? The one that's like the Hadamard and then the measurement, so the Z is flipping that as well. Okay, so it flips that as well. Mm-hmm. Okay, so what the Hadamard does is it moves the certainty around. Okay, so those are called Clifford operations. Yeah, I'm probably going a bit too quick. I've a bit too quickly over that, but I've those are things that we've seen that I've gone through already through Q Sharp's introduction, and yeah, that's good. Okay, I'm gonna change the question to qubits in certain answer. For example, I can take the state 0, then swap the black circle up to the top, then a qubit that was certain towards a 0. There's nothing say can't be 0 because that name has already been taken. Plus, okay, so here introduce the plus state, okay, which is what we're saying. Yeah, that is the plus state, and then the minus state is the equivalent, but with the one. So if we do first a next gate, and then we apply a Hadam before the Hadamard, or a Z after, we can make it stop circle. Oh yeah, of course. So it's either X and H or H and Z. Mm-hmm. Okay. Okay, that was definitely helpful. Making qubits talk to each other. As we've seen, qubits only have a limited amount of certainty in their answers to questions. When programming quantum computers, our goal is to manage that certainty as best as we can. We must guide it on a journey from input to output. So far, we haven't got many tools to help us do that. In fact, the H gate is the only one that moves the certainty around. Okay, agreed, quantum, hello, quantum. Okay, so here we talk about the control gates, and we also talked a little bit about that. And in the game, there is the control Z gate, which is introduced in level 3. I haven't gotten that far yet. I'll probably play the game a little bit more. I'm not a big fan of puzzles, but that maybe you will discover something interesting. So there are a few possible ways we can explain the effects of the control Z. Oh, that was also in the game, so I'm going to skip that. So that was also in the if you check out the video where I play the game, I basically go through the guide in the game, and they explain that already. So the two different types of how do you explain the control Z, um, which was I think maybe you should do a refresher anyway. But the idea was that it's, you apply a Z, even only if the control qubit is 1, so to say. So let me go all the way up here just quickly. I think that's exactly the same. It looks at the bottom circle, and if it's black, does a Z to the right qubit or does nothing to it? As white or black. If it's white, the left qubit is therefore effectively acting like a switch. Yeah. So in this case, the CZ, because this guy here is on. It's no, because this guy here is on. Then this is flipped. Is that the thing? No, because this guy is on. This guy is flipped. Exactly. And yeah, or that. And here there was another explanation, but with the qubits reversed, and then there is a third way of explaining that, which is quite different. It moves circles around, to swap pairs of circles. So it swaps these pairs of circles, basically. It's an interesting way to see it. So because if now I understand that this is whether the qubits agree or disagree, and in this case, if it's off, it means they agree. So it means this and this agree because they are 0. So basically, that's an interesting way of seeing it from an intuitive perspective. So it basically says I'm making a trade-off, and I'm switching the certainty of agreement. No. Or I'm just okay. So they are done. What you're saying is they are not agreeing anymore. Anyway, it's this is definitely the control Z is more complicated intuitively in that sense, but because the control X understand you flip or you don't flip, and the control Z is like you do control Z or you don't do control Z. So, but in that scenario here, for example, it seems like you could explain it as in you're switching, so you're making them go from agreeing to disagreeing, right? So from agreeing to disagreeing, that is something to prove. That's something to check whether this is what it means. So you switch, maybe intuitively you could say that. So basically you're switching the type of correlation. Maybe that's the way to say that. Control Z basically flips the type of correlation, whether it's they agree or disagree. I don't know if that's correct. Explanations now with how to travel some parts. Check what it does to the circle at the very top of the grid. So when you have that, where both there's full uncertainty, but you see the correlations that they what? Okay, so this is the confusing part, right? So what's going on between here and here? Because in my intuitive way of explaining that would be okay. So the qubits you flip. So you're saying whether they agree or disagree, but in this case, how would you say that? How would you intuitively explain that? So I mean, maybe that's the thing is you cannot because you need to take a look at what. Because I remember that they add another measurement exactly. That's this measurement. That's they were doing this in the guide as well. Um, so, but in this case, here's wide, which means well, that's confusing. Why would it be a 1? Oh yeah, because they disagree, and here they agree, right? So it basically doesn't change. Okay, I see. So what this has done is, okay, so it's not, so they basically, it just probably feels stupid. I'm trying to explain that and I cannot explain that. So probably should just move on. But it seems like here here there's like an agreement and a disagreement, and then those agreements and disagreements they move to the actual qubit states. Qubit, yeah. And here the same, right? So basically this goes here and this goes here, and this goes here and this goes here, and then this thing just, I mean, by following the rules of whether they agree or disagree, they obviously turn white and black accordingly. It's possible with understanding this effect, but if you want to become a quantum programmer, you probably like to know what's going on. So, okay, so this is okay. So let's make that a challenge. Let's make that a challenge, and so understanding the control Z, that's going to definitely be, I'm going to definitely make a video out of that. I think that can really be a breakthrough in my building up intuition. The grid not quite big enough. The 8 circles and fully describe a pair of qubits for a complete description. But that's interesting. Is this really a complete description? So, okay, so for a complete description, we need to add another possible question. The Q experience discussion can be done with the following gates: S transpose, Hadamard, and measurement. And that adds the other circle. Yeah, so that's what also where the game finished, where the thing finished, the guide in the game finished. So, and now you have full description of a qubit. It's definitely an interesting perspective to that. With this, you can solve the mystery of the control Z. Okay, challenge accepted. Yeah, let's do a video on that later on. Solve the mystery of the control Z. You can also check out how the X, Z, and H gates affect these new circles. And beyond Clifford, all the gates we discussed so far, flipping circles, black and white, but there's much more you can do with Clifford gates. There's a way to move information around in quantum computers. They're also excellent at error correction. Blah blah blah. For full quantum computation, however, we need something more. We need to move beyond circles that are just black and white, and we need ones that are mostly black, pretty much random, a bit biased towards white, and that's exactly what I meant. I think that's beautiful to go through all these examples, but really the true power comes when you mess up with this. And then it's probably more complicated to stay at an intuitive level, because you're going to have different probabilities for each of the possible outcomes. But okay, so and here it says if this, okay, the app version is just playing with those, and if you want to see, if you want to play with all these other gates, then there's a command line version. We'll do a video on that as well. The command line version, it has an extra gate called Q. Okay, beyond 2 qubits, the game Hello Quantum helps you build up intuition and knowledge with just 2 qubits. Once you have that, you can begin tackling larger numbers. Yeah, 3 qubits. Okay, so that basically tells you why it's impossible, I guess, to simulate a quantum computer. I think that was in the game as well. Oh, and that's the article that was linked in the app. Does it need to build them? Yeah, okay, cool. So definitely, I've definitely learned something, which is what does this grid in the middle mean? And that just has basically triggered more interest in trying to understand what the control Z does. I think I have an intuitive understanding, but I'm not there yet, I would say. perfect. But that's cool. So this is basically the this encodes how much those qubits agree or disagree. Um, so the entanglement, basically, that's where I was going at, I guess. Cool.